My name is Paul Callaghan, and in this series of videos we're going to be looking at some of the basic ideas behind nuclear magnetic resonance and magnetic resonance imaging. And to help us look at those ideas, we've got this apparatus here behind me. It's a very simple nuclear magnetic resonance apparatus which can demonstrate most of the basic principles we need to understand in order to appreciate what magnetic resonance imaging and nuclear magnetic resonance can do. In thinking about magnetic resonance, we'll be thinking about atomic nuclei and their behaviour in a magnetic field. And I want to start by demonstrating some of the basic physics behind the behaviour of atomic nuclei in a magnetic field. And to help me do that, I've got a mechanical device, and it's this wheel over here. The first principle of understanding atomic nuclei in a magnetic field is to realise that those nuclei have magnetism. And so, like little compass needles, when they're placed in a magnetic field, they tend to line up with the field. And I can demonstrate that idea with this wheel. There's no magnetic field that's playing a role here, but we have the Earth's gravitational field. And the effect of that gravitational field is that if I try to suspend this wheel on a string like this, it twists and finds a natural orientation pointing along the Earth's gravitational field. Why is that? Well, the combination of the weight force of the wheel and the string causes a torque to act, and that torque or twisting force reorients the wheel so that it hangs vertically. The second idea that's really important in understanding nuclear magnetism is the idea that the nuclei themselves have angular momentum. Let me demonstrate angular momentum with this wheel. I can do that simply by spinning it. Now let's try that same trick of suspending the wheel, like I did before, on the string, now that the wheel is spinning. Something really remarkable happens. That effect is called precession. And that precession idea is very, very important in understanding the way magnetic resonance works. Let's look at that precession a little more closely and see how it depends on the orientation of the axle of the wheel. I'm going to start with the wheel with its axis horizontal. It takes about a second to go around. What happens if we orient the axle slightly differently, like this for example? It takes about a second to go around. In fact, it doesn't matter what orientation we have this axle, the precession frequency is pretty much the same. However, if we do suspend the wheel in that natural low energy position, the precession is very, very hard to see. If we tilt it a bit, it reappears. So we have to have the axle of the wheel tilted from the vertical in order to see the precession. By the way, there's another position where the precession is very hard to see as well, and that's with the axle pointing up like this. But anywhere in between, pointing up and pointing down, the precession is very visible. By the way, these two states of pointing down, pointing up, turn out to be very relevant in the case of the atomic nuclei that we'll be looking at in these series of videos, and that's the hydrogen nucleus. It turns out that the hydrogen nucleus has two very natural states in a magnetic field, one pointing one direction and one pointing in the other direction. So what have we learned here? We've seen that in order to observe the precession, we need to have the axle tilted at some angle away from the vertical. And that begs the question, if we did start in that low energy position with the axle pointing vertically downwards, how could we disturb it in such a way that we could make the precession visible? And I want to demonstrate that to you. Just watch this trick. I did it. I used my finger to apply a torque to the wheel that brought the axle away from the vertical position into the horizontal. What was the basic idea behind the trick? The first thing is that I had to apply the torque in the horizontal plane. I had to apply it in a direction normal to, or at right angles to, the torque that the Earth's gravitational field is applying. The second thing is that I had to move my finger around in synchrony with the wheel, keeping the reorientation of that torque from my finger at the same frequency as the precession frequency. Let me just demonstrate that again. So this movement of the torque following exactly the precession frequency of the wheel is known as resonance. The frequency is exactly the same in both cases. And the idea of resonance is really central to what we'll be looking at when we reorient atomic nuclei from their natural equilibrium states in a magnetic field. So that's wheel mechanical resonance. When we perform nuclear magnetic resonance, we have to do the same trick. We have to apply a torque that's orthogonal to the torque of the magnetic field on the spins, and we have to have that torque varying with time or oscillating in exact frequency match with the natural precession frequency of the nuclear spins. And how do we apply that torque? We do it with another magnetic field. A magnetic field that's orthogonal to the main magnetic field that tries to orient the spins, and a magnetic field that's oscillating in time in exact synchrony with the precession frequency of the atomic nuclei. And that is nuclear magnetic resonance. There's one more thing I want to show you. Let's go back to the wheel. Suppose we do this wheel mechanical resonance and end up with the axle pointing in a direction that really shows the precession very nicely. The horizontal orientation as shown here. Let's look what happens with time. Gradually the wheel reorients and the visibility of the precession starts to die away. This returning to some sort of equilibrium is something we'll also see happening with atomic nuclei.